In this video, we are going to talk about an important topic of bases. This is our overview slide, which we'll spend a few minutes on before we get to the main part of our video where we go over this topic in more detail and with more examples. We will start by defining what a basis is. A basis of V is a list of vectors in V that is both linearly independent and also spans V. There are many examples of bases. We're going to go and work in detail and show that each of these bases both are linearly independent and span the space. Once we go through a number of these examples, we'll do more examples by doing the proof of these theorems, which also a couple of them are extremely useful. The first theorem is a list of vectors, v1 through vn, in a vector space V is a basis for V if and only if every vector in V can be written uniquely as a linear combination of our list of vectors. Second, we have the spanning list contains a basis theorem, and it says every spanning list in a vector space can be reduced to a basis of the vector space. So in other words, the spanning list will contain a vector space, but it'll have too many because some of our vectors will be linearly dependent. So when we eliminate the dependent vectors, we'll be left with a basis. The next theorem, every finite dimensional vector space has a basis. And then we have this theorem, linearly independent lists extend to a basis. So every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis. This kind of goes with this spanning list contains a basis. This one, we eliminate extra dependent vectors until we get a basis. This one, we expand the list. So we have a linearly independent set. So we just keep adding more linearly independent bases until we span the space, and then we will have a basis. Last, basis length does not depend on bases, so two bases for the same vector space will have the same number of vectors, which leads us to define dimension. The dimension, denoted dim V of a finite dimensional vector space, is the length of any basis of the vector space. In other words, dimension is the number of vectors in a basis. That wraps up our overview, so we'll go to the main part of our video. We'll start by talking about bases and going through these examples and proving they are all bases, or in this case, proving it's not a basis, by showing linear independence and spanning. I will keep these two comments at the top of the page for your reference. First, a basis of a vector space V is a list of vectors in V that is both linearly independent and spans V, so you want to remember there are two things we need to show. If we want to say something is a basis, it needs to be linearly independent, it needs to span. In our last video, we did quite a few examples of showing how things are linearly independent. So in this video, we're going to start talking about showing how vectors span a space. So to show a list of vectors span a vector space, we need to show how an arbitrary vector in V is a linear combination of the list of vectors. These are the examples we're going to do. These are the examples listed in your book. There's one more example of a basis listed in your book, and we're going to save that for later on in this video to illustrate one of the theorems. The first example, we want to show that the standard basis of Fn is a basis, and the standard bases look like vectors that have zeros in all positions except the ith position. So in other words, E1, this is what we call E1. It's our first in our standard bases, has zeros in all positions except the first. So here's 1, the first position, everything else is 0. E2, this will be our second standard basis, has zeros everywhere except in the second position because it's E2. E3, and we don't show this here, E3 then is going to have zeros in all positions except the third position, E4, etc. Until you get up to En, it's going to have zeros in all positions except the nth position. And this is called the standard basis of Fn. The first thing we need to show is that these vectors are linearly independent. So I'm going to set up my equation. That's the homogeneous equation. So I'm going to set up scalar a1 times e1 plus scalar a2 times e2 up to scalar an times en, and then I set that equal to the 0 vector. This one's fairly straightforward. I don't need to get it in matrix form because if I look at this, I multiply a1 times this vector and I'm going to get a1 in the first position. When I do this multiplication, the scalar multiplication, I get a2 in the second position. So essentially I get an in the nth position. So when I add all the left-hand side together, I'm going to get a1, a2 up to an, and then I set it equal to my 0 vector, and that tells me that a1 equals 0, a2 equals 0, all the way up to an equals 0. So everything, all the scalars are equal to 0, which means these vectors are e1, e2, e3, up to en are all linearly independent. Next, we need to show that these vectors span our space. And again, our space here in this example is Fn. So I need to show what an arbitrary element of Fn looks like, and then write that arbitrary element as a linear combination of our vectors. Again, to show a list of vectors span, in this case Fn, we need to show how an arbitrary vector in Fn is a linear combination of e1, e2 up to en. So let me write this. My arbitrary vector then of Fn is equal to x1, x2 up to xn. And you can use whatever variable you want, but I happen to like x. To show again that these vectors span, we have to show that our vector, our random vector, is a linear combination of the list of vectors. So my random vector, x1, x2 up to xn, this is just x, is equal to some linear combination of e1, e2 up to en. And I was going to put a1, because I'm solving for it, but look at it. And you can see that what I need to do is multiply my first coordinate times e1, multiply my second coordinate times e2, up to my nth coordinate times en. And this is how it's a linear combination. So the ith coordinate of my x vector, which is x sub I, is the scalar multiple for e sub I. So therefore x is in the span of the standard bases, and finally then the standard bases, because it's both linearly independent and spans V, is a basis for Fn. My next example is to show the list 1, 2, and 3, 5 is a basis of R2. And when they say the list, they mean the list of vectors. There's 2 vectors in here, 1, 2, and 3, 5. The first thing to do is set up my equations to show linear independence. So it's a scalar times my first vector, 1, 2, plus a scalar times my second vector, 3, 5, is equal to 0, 0. Again, this is my homogeneous equation. Now here's the matrix we're going to use to solve this vector equation. So we have the first vector 1, 2, the second vector 3, 5, and then we put the 0, 0 here. We row reduce. This one's pretty easy to row reduce by hand, but you can also use Wolfram alpha. This here back into vector form. So we have our coefficient matrix, our variable a, and then our solution here. So reading this, we have multiplying this row times the column, we have a1 plus 3a2 equals 0, and then here we have minus a2 equals 0. I actually did this backwards. I did it from the bottom. So I have minus a2 equals 0, which suggests that a2 is equal to 0, which is why over here I just did a1 and then 3a2, that's just 0. So a1 is equal to 0. But the short of it is both a1 and a2 are 0, which means our two vectors are linearly independent. To show that the two vectors span R2 is our vector space, I'm going to choose my arbitrary vector chosen from R2, and I'm going to show that it can be set equal to a scalar times my first vector 1, 2 plus a scalar times my second vector 3, 5. The matrix that represents this vector equation then is our first vector 1, 2, our second vector 3, 5, and then our solution vector x1, x2. So at this point, again, I couldn't use Wolfram alpha, but I did this by hand. I row reduced till I got to this equation. Back in vector form, then I have my coefficient matrix, my variable a, and then my solution x1 minus 2x1 plus x2. Now because this matrix was gotten by row reducing this matrix, the system of equations represented by this matrix has the same solutions as the system of equations represented by this matrix. So now this is what we have to solve. And just a note, before I was telling you for the most part in this class, we're going to row reduce by using Wolfram alpha. This one I don't think you can. So I'm going to say most textbooks will have how to do this row reduction, and these are pretty straightforward and simple. But if you need a review or you need a tutorial on how to do this, I do have a series called Linear Algebra in 5 hours or less. This first video will tell you how to do this row reduce a matrix into echelon form. I don't even bother getting it to reduced echelon form, just row reduced echelon form. Just echelon form is good enough. Here it is. It's a 34-minute video. You could probably not watch all the examples, and you can watch it at 1.5 speed, so it'll probably take you like 12 minutes to learn. Here we are with our new system of equations. When we multiply the row times columns, we get a1 plus 3a2 equals x1. Multiplying this row times column, we get 0a1 minus a2 is equal to minus 2x1 plus x2. So I had that here. Minus a2 is equal to minus 2x1 plus x2. So this over here tells us what x2 is. Here I saw for a1 is equal to x1 minus 3 times, and then I plug in what I have for x2 here, and so it becomes minus 5x1 plus 3x2. So once someone gives us the vector x1, x2, a particular vector, we can solve for the coefficients that go in front of 1, 2, and 3, 5. So we can show how it's a linear combination of these two vectors. And I went ahead and wrote that out. So our x1, x2 is equal to a1, which is this minus 5x1 plus 3x2 times our first vector, 1, 2, plus a2, which is our 2x1 minus x2 times our next vector, 3, 5. And you know, it's kind of nice because we can do a little sanity check. So this isn't a proof that it works for every x1 and x2, but I could choose one with small numbers just to give me a nice, warm, fuzzy feeling. So I looked and said, well, what if my vector x was 2, 1? And then I plugged in 2, 1 here. So I have 5 times 2, or negative 5 times 2, which is negative 10, plus 3. So that's negative 7 times 1, 2. And over here I have 2 times 2, which is 4, minus 1, which is 3 times 3, 5. And if you multiply this out, this is minus 7 plus 9. That gives us our positive 2. This is our minus 14 plus 15, that gives us our 1. So this gives me a good feeling that I've done all my algebra right. And so what we can say is here we've shown that any x, vector x, can be written as a linear combination of 1, 2, which means that x is in the span of 1, 2, and 3, 5, which means 1, 2, 3, 5 span our space R2. Since the two vectors are linearly independent, and because they span, that means 1, 2, 3, 5 is a basis for R2. Oh, and there's one other comment, and that is there can be more than one basis for a space. So here we have 1, 2, 3, 5, and we found it's a basis for R2. But remember the standard basis, right, is also a basis for R2. The standard basis being E1, which is 1, 0, and E2, which is 0, 1. That's also a basis for R2. And then we have another basis, 7, 5, negative 4, 9 is also a basis for R2. I haven't proven this, but there can be more than one basis for a space. And when we talked about dimension, we introduced that idea in our overview. All your bases for R2 are going to have the same number of vectors. In other words, all your bases are going to have 2 vectors. All your bases for R2 will have 2 vectors, and the number 2 then becomes the dimension of the space, which is why we say R2 is 2-dimensional. So we can keep going all day. Oh, but we're going to do this example, which is to show that the list 1, 2, negative 4, 7, negative 5, 6 is linearly independent in F3, but is not a basis because it does not span F3. So we'll look and see what it looks like when something does not span. But we're going to start with linearly independent. So we're going to set up our homogeneous equation, our scalar a1 times our first vector, 1, 2, negative 4, plus our scalar a2 times our second vector, 7, negative 5, 6, set it equal to our 0 vector. So the matrix that represents this is going to be our first vector, 1, 2, negative 4, our second vector, 7, negative 5, 6, and our solution vector, 0, 0, 0. We row reduce, and we get this matrix with columns 1, 0, 0, 0, 1, 0, and 0, 0, 0. So this represents our new system of equations, which is our coefficient matrix 1, 0, 0, 0, 1, 0 times our variable a1, a2, and our solution 0, 0, 0. And what we see, this is pretty straightforward. When we do our row times column, we get a1 plus 0, a2 is equal to 0, which means a1 is equal to 0. And then here we have 0 times a1 plus a2 is equal to 0, which means a2 is equal to 0. And at the bottom, we have 0, a1 plus 0, a2 is equal to 0. Well, that's great. But anyway, what we have is a1 and a2 have to equal 0. That's our only solution. And therefore, our two vectors are linearly independent. And the next thing we need to do is show if it were a basis, it's going to need to span our vector space F3, but we're already told that it's not a basis because it does not span, but let's verify that. So we're going to take our arbitrary vector in F3, that looks like our x vector, x1, x2, x3. We're going to set it equal to a scalar times our first vector, 1, 2, negative 4, plus a scalar times our second vector, 7, negative 5, and 6. The matrix that represents this vector equation has the vector 1, 2, negative 4, this next vector 7, negative 5, 6, and then the solution vector x1, x2, x3. And I row reduced this by hand so you can see, what did I do for this first? I multiplied this top row by negative 2 and then added together. So I get 0, negative 19, minus 2x1 plus x2. And for the bottom, the first step I did is I multiplied this top row by negative 4 and then added the first and third rows together, and I got 0, 34, and 4x1 plus x3. To eliminate this 34, I multiplied this the second row by 34 over 19. So I got a 0 here when I multiply this by 34 over 19 and add it to our 4x1 plus x3, I got negative 8 over 19 x1 plus 34 over 19 x2 plus x3. So many complicated fractions. I don't know why it had to be so difficult. But anyway, now I'm going to put this back into vector equation form. I have my coefficient matrix with columns 1, 0, 0, 7, negative 19, 0, my unknown, my variable, a1, a2. And then for my solution vector, I have for the first coordinate x1, the second coordinate is minus 2x1 plus x2, and the third coordinate is minus 8 over 19 x1 plus 34 over 19 x2 plus x3. So the equations I have, multiplying this row times column, I get a1 plus 7a2 is equal to x1. That's for my first coordinate. This next row times column, I get 0 times a1 minus 19a2, which is here, is equal to my minus 2x1 plus x2, which means a2 is equal to minus 1 over 19 times minus 2x1 plus x2. And then finally I have 0 times a1 and 0 times a2 is equal to this third coordinate, minus 8 over 19 x1 plus 34 over 19 x2 plus x3. And if you look at this last equation, so let's not even worry if I got my arithmetic right here. Look at this last equation. We're saying that 0 times a1 plus 0 times a2, so this is 0, over here is equal to some linear combination of x1, x2, x3. And here x1, x2, x3 represents an arbitrary vector in F3. So we cannot depend on x1, x2, and x3 all equaling 0. So if x1, say, for example, equaled 1, this would be an impossible equation to solve. So for a general x1, x2, x3, this equation has no solution, which means these two vectors do not span F3, and therefore it is not a basis. Did you ever wonder why it says bases here and it says bases here, but they're spelled differently? So bases is the plural, the B-A-S-E-S. The B-A-S-I-S, bases, B-A-S-I-S, that's the singular. It's a basis for a vector space. This is, in general, many bases. It took me years to figure that out, but now you have the benefit of my wisdom. Our next example is the list 1, 1, 0 and 0, 0, 1. And we want to show that it's a basis, first of all, there's no way this is going to be a basis for F3 because the standard basis F3 has E1, E2, E3, and we already said that all the bases are going to have the same number of vectors. So we know this isn't a basis for F3, but it's going to be a basis for vectors in F3 that look like X, X, Y. In other words, the first and second coordinates are the same. And now that we're getting the hang of it, I'm just going to put everything out there. So to show that it's linearly independent, we're going to put a scalar times our first vector, 1, 1, 0, plus a scalar times our second vector, 0, 0, 1. And that's equal to 0, 0, 0, our homogeneous equation represented by this matrix, our first vector 1, 1, 0, our second vector 0, 0, 1, and our solution vector 0, 0, 0. This row reduces, actually, it's already row reduced. So we put it in vector form again, our coefficient matrix times our variable times our solution vector. Multiplying row times column, we get A1 equals 0. Multiplying row times column, we get the same statement, A1 equals 0. Multiplying row times column, we get A2 is equal to 0. Therefore, the two vectors are linearly independent. To show that we span the vectors x, x, y, we're going to put our representative element x, x, y is equal to a coefficient times 1, 1, 0 plus a scalar coefficient times our second vector 0, 0, 1. And you can, put this in matrix form and row reduce it, but it's kind of easy to see, or maybe if you just take a minute and look at it, you can see if you multiply, make A1 equal to x and A2 equal to y, you're going to get your solution for x, x, y is equal to x times 1, 1, 0 plus y times 0, 0, 1. Which means 1, 1, 0 and 0, 0, 1 spans the subset of vectors of the form x, x, y in F3. And finally, because 1, 1, 0 and 0, 0, 1 are both linearly independent and spans this space of x, x, y, it's a basis for the subset of vectors x, x, y in F3. Our next example is the list 1, negative 1, 0 and 1, 0, negative 1. Again, we're in R3, so there's no way this is a basis, but we have 1, negative 1, 0, 1, 0, negative 1 is a basis for vectors of the form x, y, z in F3, where x plus y plus z equals 0. First, we're going to show the two vectors are linearly independent, so we have a scalar times our first vector, 1, negative 1, 0, plus a scalar times our second vector, 1, 0, negative 1 equals our 0 vector. So in matrix form, we're going to have our first vector, 1, negative 1, 0, our second vector, 1, 0, negative 1, and our solution vector, 0, 0, 0. This row reduces to the matrix with columns 1, 0, 0, 1, 1, 0, 0, 0, 0. So back in vector form, we have our coefficient matrix with columns 1, 0, 0, 1, 1, 0, our variables A1, A2, and then our solution 0, 0. Multiplying row times column, we get A1 plus A2 is equal to 0. Here we have that 0A1 plus A2 is equal to 0, and then here we have 0A1 plus 0A2 is equal to 0. But we're going to start with, then we have A2 is equal to 0, and because A1 plus A2 is equal to 0, that means A1 is equal to 0, so both are equal to 0, meaning the two vectors, 1, negative 1, 0, and 1, 0, negative 1, are linearly independent. To show that these two vectors span the space of vectors that are the form x, y, z in F3, where x plus y plus z equals 0, we need to find a way of expressing the general form of this vector, x, y, z, where x plus y plus z equals 0. And a little bit of thought will mean that basically we can make our third coordinate, z, dependent on x and y. So in other words, our general form of this vector is going to be x, y, and then z is going to be equal to minus x minus y. So that's what I have here. And you can see, since this is the z coordinate, right, we set it equal to minus x minus y. When we bring the x over, we bring the y over, we get z plus x plus y equals 0, which is exactly what we want over here. Now we write our general form of our vector. xy minus x minus y is equal to a coefficient times our first vector 1, negative 1, 0, plus the scalar times our second vector 1, 0, negative 1. In matrix form, we have our first vector 1, negative 1, 0, our second vector 1, 0, negative 1, our solution vector xy minus x minus y, and then here I row reduced. This first step I did is I replaced R2 with R2 plus 1, so I added these two rows together to get this one. For my second step, I replaced R3 with R3 plus R2, so I get this matrix here. And this is my row-reduced matrix. Putting this back into vector form, I have my coefficient matrix 1, 0, 0, 1, 1, 0. My variable A1, A2 is equal to, over here I have my solution x, x plus y, and 0. Multiplying out, I get A1 plus A2 is equal to x. And here I get 0A1 plus A2 is equal to x plus y. Here I got 0A1 plus 0A2 is equal to 0. So what this tells me is A2 is equal to x plus y, and A1 is equal to x minus A2, which is equal to minus y. So this tells me, given an x and a y, I can find the coefficients. Well, first of all, I can find what z is, and then I can find my coefficients a1 and a2 to write this vector as a linear combination of 1, negative 1, 0, and 1, 0, 1, which means these two vectors span this space. But I'm going to pause just for a minute to do a little sanity check. Let's say my x, y, and z is equal to 1, 2, and negative 3. Does that make sense? My x plus y plus z does equal to 0. So according to this would say my a1 is equal to negative y. So it's going to be minus 2 times my first vector, 1, negative 1, 0. And then my a2 is going to be x plus y. So that's going to be 3 times my second vector, 1, 0, negative 1. So when I multiply negative 2 times 1, I get negative 2 plus 3 is equal to 1. When I multiply my negative 2 times negative 1, that gives me 2 plus 3 times 0. Still, I'm left with 2. And then finally, negative 2 times 0 is 0. 3 times negative 1 gives me my negative 3. So at least it looks like I did all my algebra correctly. Again, it's not a proof, but something to give you a warm, fuzzy feeling about your algebra skills. And so what we've said, even though we already knew that over here without the sanity check, we are going to say that the two vectors spans the subsets of vectors that look like x, y, minus x minus y. And since the two vectors 1, minus 1, 0, 1, 0, minus 1 spans our space for x, y, z, where x plus y plus z equals 0, these two vectors are a basis. Our last example for this set of examples, because there's a bunch more, they're more proof-oriented after this. Well, these are actually kind of proofs too, but they're even more proofy. Anyway, our last example from this list is the list 1, z, z squared, z cubed, z to the fourth, all the way to z to the m, is a basis for polynomials of degree m or less. It is fairly straightforward to show these are linearly independent because I'm going to multiply my scalar times my first vector 1 plus my next scalar times my second vector z plus another scalar times my second vector z squared all the way up to my mth scalar times my mth vector z to the m and set it equal to 0. You know, from algebra, when you have these polynomials, you know that you set like terms equal to 0, so this, because it's equal to 0, this is going to be 0, this is 0, this is 0, and this is 0. What we can conclude from algebra is that all of our scalars now is equal to 0, so our vectors now are linearly independent. I feel like working with polynomials as a space is easier. Now to show that these vectors span the space of polynomials, we're going to take our arbitrary polynomial from this space. So we're going to have some constant c naught plus a scalar times z plus another scalar times z squared all the way up to c sub m times z to the mth power. So this is our arbitrary polynomial of degree m or less. And the question is, can p of z, then this polynomial, this random polynomial or arbitrarily chosen polynomial, be expressed as a linear combination of our vectors 1, z, z squared up to zm, And the answer is, well, of course it can, because that's just what we did over here. I suppose technically we can write P of z is equal to a linear combination of our vectors 1, z squared up to zm, and you can see then a naught becomes c naught and a1 becomes c1. It's not, this one's really easy. It's almost too easy. So what we say, it's almost so easy, it's like there's nothing to do, which is almost confusing. So we say yes, these vectors, 1z, z squared up to zm, spans the set of polynomials of degree m or less. And since this list of vectors here, 1z, z squared up to zm, is both linearly independent and spans our space, then it is a basis for our space of polynomials of degree m or less. Now that we have a pretty good feel for bases, we have this first theorem, a criteria for a basis. So a list of vectors in a vector space is a basis for the vector space if and only if every vector in the vector space can be written uniquely as a linear combination of our list of vectors. I've kept this definition of basis up here for your reference, and then I have our criteria for a basis theorem that we're going to do a proof of. And the first thing to note is because of this if and only if, there are going to be two parts of this proof. The forward direction, where we assume this part here, a list of vectors is a basis of V. So v1, v2 up to vn is a basis for V. And that should imply in the forward direction that every V in the vector space can be written uniquely as this linear combination. So V equals a1 v1 plus a2 v2, and that this representation is unique. The other direction is this way. So we assume this part here. We're going to assume that V is equal to a1 v1 plus a2 v2 up to an vn. That's a unique representation. So again, kind of the opposite direction. We have our linear combination representation is unique, and that's going to imply, this direction, that the vectors is a basis. We are going to start with the forward direction, which is over here. We are given then that v1, v2 up to vn is a basis for V, and we want to conclude that we have this linear combination representation that is unique. Well, since v1, v2, vn is a basis for V, that means v1, v2 up to vn spans V. Just by definition of a basis, right? The two things it does, they're linearly independent and they span your space. If this set of vectors spans the space, that means for all vectors in V, all the vectors are in the span of v1, v2 up to vm, which means all vectors in V can be written as a linear combination. So we have V, our vector V, is equal to a1 v1 plus a2 v2 up to am vm, and that's just the definition from the definition of span. So we have this now, we have this linear combination. So the next thing we need to show is that linear combination is unique. To show the representation is unique, we're going to assume we have one representation, V equals c1 v1 plus c2 v2 plus cm vm. We're going to assume then we can find a second representation, but we're going to show that the second representation by necessity has to equal the first representation, which means the representation here was really unique. So for now, we're going to assume we have this second representation, the same vectors, v1, v2 up to vm, but different scalars, so a1, a2, am. But now the next thing we're going to do is subtract this representation over here from this representation. So subtracting on the left-hand side, v minus v gives us 0. Subtracting the right-hand side, now we're going to get c1 minus a1 times v1 plus c2 minus a2 times v2 up to cm minus am times vm. But what this tells us, since this is all equal to 0, all these coefficients in front of our vectors must equal to 0, which means that c1 must equal to a1, c2 must equal to a2, all the way up to cm must equal to am. And therefore, our two representations are the same, so our representation is unique. Now that we've shown this forward direction, we're going to work on this opposite direction. So we're given that there's this unique representation of V as a linear combination of our v1, v2 up to vm. So I copied that down. For every vector in our vector space, there exists this explanation point means unique. So, and this backwards E means there exists. So there exists a unique V equals A1 V1 plus A2 V2 up to AM VM. What we want to conclude then is our V1 V2 up to VM is a basis. And first, I'm going to say that from this definition, since we've written V as a linear combination of V1 V2 up to VM, that means V is in the span of V1 V2 up to VM. And now since V was arbitrarily chosen from our vector space, that means V1, V2 up to VM spans our vector space V. Remember, there are only two things now to show that this set of vectors is a basis for V, and that is that they're linearly independent and they span V. We've already shown that they span V, so what's left now is to show that this set of vectors, V1, V2 up to VM, is linearly independent. To show a set of vectors is linearly independent, we look at the homogeneous equation. In other words, we write our vectors as a linear combination, set it equal to 0. Clearly, the trivial solution is a solution. The question is whether or not it is the only solution. But that is already answered for us here because it says every representation is unique. That is, since we're given the representation is unique, the equation, the homogeneous equation, has only the trivial solution, and therefore our vectors V1, V2 up to Vm, our set of vectors, is linearly independent. You can say our vectors are linearly independent, or the set is linearly independent, which means our V1, V2 up to Vm spans V, it's linearly independent, and a basis for V. So we've finished proving the opposite direction. We've now completed part 1 and part 2 of our proof, and we are done. And let's just take another look at this. What does this say? That a list of vectors is a basis if and only if every vector has a unique representation. So that's kind of an interesting theorem, but I have to tell you, it doesn't come up a lot, but it does, I believe, come up in the proof of our next theorem, maybe. This next theorem is that a spanning list contains a basis. The idea is if you have a list that spans, it may not be a basis because it may not be linearly independent. So you may have some dependent vectors that if you throw them out, you can have a linearly independent list, and then you'll have a basis. So every spanning list in a vector space can be reduced to a basis of the vector space. Here's my theorem, and we're going to do the proof. Again, every spanning list in a vector space can be reduced to a basis of the vector space. And if the vectors are independent, well, we already have a basis because it spans and it's independent. If the vectors are not linearly independent, we're going to remove vectors that can be written as a linear combination of the others. This is really the crux of our proof. I guess you can say it more formally, but this is where I'm going to leave it, but I will do an example to show you. We are going to use this example to illustrate this theorem that every spanning list in a vector space can be reduced to a basis. Our list of vectors is going to be the vectors 1, 2, 3, 5, and 4, 13, and R2. The first thing we're going to do is show that these three vectors, 1, 2, 3, 5, 4, 13, span R2. So we're going to take an arbitrary vector chosen from R2, we'll call it X, with coordinates x1, x2. We're going to try to write it as a linear combination. So A1 times 1, 2, plus A2 times 3, 5, and A3 times 4, 13. The matrix then we use to represent this set of vector equations is the vector 1, 2, the vector 3, 5, the vector 4, 13, we still have our vectors, so I went ahead and showed the vector equation A1, A2, A3 equals our solution. So our matrix, we're going to combine our coefficient matrix, 1, 2, 3, 5, 4, 13, and then our solution vector, x1, x2. We row reduce this to this matrix here. It's the matrix with columns 1, 0, 3, -1, 4, 5, x1, and then minus 2x1 plus x2. Putting this back into vector form, we have our coefficient matrix 1, 0, 3, -1, 4, 5. Our unknowns, our variables A1, A2, A3. And it's equal to our solution, which is x1 minus 2x1 plus x2. Multiplying row times column, we get A1 plus 3A2 plus 4A3 equals X1. That's this first equation. Multiplying this row times this column, we get 0A1 minus A2 plus 5A3 equals this minus 2X1 plus X2. That's this equation here. Solving then for A1, we get A1 is equal to X1 minus 3A2 minus 4A3. Solving for A2 over here, we get A2 is equal to 5A3 minus 2X1 minus X2. And A3, this is an underdetermined system, so A3 is free. We can choose it to equal whatever we want. So there are multiple solutions to this. And we're going to choose A3 equals 1 because that's easy to work with. So writing x1, x2 as a linear combination of 1, 2, and 3, 5, we're going to put 1 in front of 4, 13. Solving for A2, now A3 is equal to 1, so we have 5 plus 2x1 minus x2. And so I'm going to write that as my coefficient in front of my 3, 5. And finally, my coefficient for A1 is x1 minus 3A2 minus 4A3, and A3 is equal to 1, so it's minus 4 times our vector 1, 2. And I can also replace this A2 here with this form so that I can get rid of A1 and A2 and only have our A1, A2, and A3 in terms of constants in x1, x2, but I just left it in this form for now. And the nice thing about these equations, we can do a sanity check. So if our x1, x2 is equal to 1, 2, I know I almost always use 1, 2. I guess using zeros is too easy, using all ones is just too easy, or too special. So I make 1, 2 my kind of default. So again, my scalar multiple for my last vector 4, 13 is 1, because A3 is 1. Now I plug in for my next scalar times 3, 5. That's going to be 5 plus 2 times x1. x1 is 2, so 5 plus 2, that's 7, minus x2, so minus 2. So I'm back to 5. So 5 times 3 fifths, or 3, 5. And then over here, in front of my 1, 2, I'm going to have x1, that's 1, minus 3 times a2, so that's going to be 3, that's minus 15. So I'm going to have minus 14, minus 4, so that's minus 18. Now now that I've calculated my a1, a2, and a3 that I had solved or provided equations for, I can double check my 1, 2 now. So here I have minus 18 plus 15. So far I have minus 3 plus 4, that's 1, which is exactly what I have. It's my first coordinate. Now minus 18 times 2 is minus 36, plus 25 is going to be 11, plus 13, that's going to be 2. So that's what I have here because it's a minus 11, plus 13 is a 2. So my sanity check says, it gives me a warm feeling about the arithmetic I've done here. So I believe I have my A1, A2, and A3 figured out for a arbitrarily chosen x1, x2. And I'm going to conclude that the vectors 1, 2, 3, 5, and 4, 13 span R2. To be a basis now, these three vectors must be linearly independent. So I set up my homogeneous equation, my scalar A1 times my first vector 1, 2, plus my scalar A2 times my next vector 3, 5, plus my scalar A3 times my third vector 4, 13 set equal to my 0 vector. This is the matrix that represents this vector equation. So I have my first vector 1, 2, my second vector 3, 5, my third vector 4, 13, and my solution vector 0, 0. I row reduce and I get the matrix with columns 1, 0, 3, negative 1, 4, 5, 0, 0. Writing this back in vector form, I have my coefficient matrix with columns 1, 0, 3, negative 1, 4, 5. I have my unknowns or my variables A1, A2, A3, and I have my solution matrix 0, 0. So this gives me the equation multiplying this row by this column, A1 plus 3A2 plus 4A3 equals 0. That's this equation here. And my second equation, I get 0A1 minus A2 plus 5A3 equals 0. That's this equation here. I solve for this, and again, this is underdetermined. I have 3 unknowns, A1, A2, A3, but only 2 equations. That means A3 is left free. So I'm going to choose A3 equals to 1, as I always do. Then I can solve for A2 is equal to 5. And where's A1 is equal to then my minus 4 minus 3 times 5, so that looks like minus 19. So I have A1 minus 19 times 1, 2. My A5 times my second vector 3, 5 plus 1 times 4, 13 equals 0, 0. And if you multiply this out, you'll see that this is correct, that my minus 19, 5, and 1 were correct choices. So I have a solution to the homogeneous equation that is not the trivial solution, meaning these three vectors, 1, 2, 3, 5, and 4, 13, are linearly dependent. And I'm going to write my 4, 13 as a linear combination of 1, 2, and 3, 5. Just using this equation, I'm going to move over my 19 times vector 1, 2, so it becomes positive 19 times vectors 1, 2, and I'm going to subtract minus 5 times 3, 5 on both sides of the equation, so that, cancels here, and I get minus 5 times my 3, 5. So this is 4, 13. It's a linear combination of these two vectors, and so I can get rid of this and still have the same span. And now we have the vectors 1, 2, 3, 5 that are linearly independent, and they span the same space as the original 3. So 1, 2, 3, 5 is a basis. As far as 1, 2, and 3, 5 is linearly independent, you can verify that on your own, but I'm also going to say, remember when we talked about how all bases have the same number of vectors, and R2 is spanned by the standard bases of E1, E2, so you need two vectors to be linearly independent. I guess a few other chapters away, we're going to say if we have two vectors that span, and the bases, the dimension is 2 and the basis has to be 2, then this must be a basis. So I guess for now I'm going to say take my word for it, and later you'll have the theorems to be able to say this is linearly independent, or if you'd like, go ahead and set up the equations. It's probably pretty quick to verify. Probably in the amount of time I talked about it, I could have verified these were linearly independent. So now you have 1, 2, and 3, 5 are linearly independent, and they span, and therefore they are a basis for R2. Our next theorem, bases of finite dimensional vector spaces. Every finite dimensional vector space has a basis. I would skip this proof, but it goes so fast. Here's our theorem. Every finite dimensional vector space has a basis. And the proof is a vector space is called finite dimensional if some list of vectors in it spans the space. And then by our last theorem, every spanning list in a vector space can be reduced to a basis. Our next theorem is another important theorem that says linearly independent lists can extend to a basis. So the idea is to form a basis, you need to be linearly independent, but if it doesn't span, we need to add some more vectors until it spans. And we need to add them in a way that we're only adding linearly independent vectors, so that every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis. And again, here's our theorem. Every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis. So let's look at two lists. First, we're going to look at the list U that consists of the vectors U1, U2, UM. They're linearly independent in a vector space. Let's let W be the list W1, W2, Wn, be a basis for our vector space. And we know because it's a finite vector space that there is a basis. That was our last theorem. Now, we know if we concatenate these two lists, so U1, U2 up to UM, W1, W2 up to UN, that they span V because it contains a basis, and the basis itself spans V. And of course, it has all this extra stuff. You could get rid of this extra stuff and you get back your original basis, but the idea is we want to expand this list here, the U list, to become a basis. And what we are going to do is we're going to pick a WJ, one of these W's. So if WJ is in the span of the U1, U2 up to UM plus the remaining J minus 1 W vectors, then we're going to remove WJ. And we're going to repeat this process until the list is independent. We're going to illustrate this theorem and that technique with this example. So we have the vectors 2, 3, 4. and 9, 6, 8. They're linearly independent in F3, but they don't form a basis because remember, a basis for R3 and F3 needs 3 vectors because, right, R3 has 3 vectors. So there's no way this spans F3. And we know that the problem is spanning because we're given that they're linearly independent. So now we're going to consider our standard bases in F3. That's E1, E2, and E3. So this is a basis for F3. So we're going to use these two lists, our 2, 3, 4, and 9, 6, 8, and we're going to extend it using our standard bases until it is a basis. So we're given 2, 3, 4, 9, 6, 8 does not span F3, so we're going to expand it, throwing in a basis. So now we know it spans F3, but it is not linearly independent. We have way too many vectors. Well, we have too many vectors. We know that because just these 3 alone span the space, so we don't need these 2. But of course, if we get rid of these 2, we're back to our original problem. The idea is we need to augment the 2, 3, 4, and the 9, 6, 8 to be linearly independent and spanning F3. And what I did is I chose at random my first vector, 1, 0, 0. And I looked to see if it was a linear combination of 2, 3, 4, 9, 6, 8, and 0, 1, 0, and 0, 0, 1. So here I have my scalar times my first vector, 2, 3, 4, my scalar times my second vector, 9, 6, 8, my third scalar times my next vector, 0, 1, 0, and my fourth scalar times my last vector, 0, 0, 1. And I just chose this one at random to think maybe I could write it as a linear combination of the other 1, 2, 3, 4 vectors. I'm going to test this out. I have my matrix now, my first vector, 2, 3, 4, my second vector, 9, 6, 8, my third vector, 0, 1, 0, my fourth vector, 0, 0, 1, times my coefficients or my variables, A1, A2, A3, A4, and that's equal to my solution vector. I want to know if it's a linear combination of 1, 0, 0. I have my augmented matrix, again my coefficient matrix with my solution matrix. I row reduce to get the matrix with columns 1, 0, 0, 0, 1, 0, 0, 0, 1, 9 twentieths, minus 1 tenth, minus 3 fourths, and the last column minus 2 fifths, 1 fifth, and 0. Looks kind of scary because of all these fractions. But one thing I'm going to say, because now our matrix has all numbers, you can plug this into Wolfram Alpha. It'll work out these horrible, actually they're not that terrible, but it'll work out these fractions for you. Now I'm going to let, this again is an underdetermined system because we have 4 unknowns and 3 equations. So I'm going to let A4 equal to 1. It is a free variable. According to our first row here, we have A1 plus 0A2 plus 0A3 plus 9 twentieths A4 is equal to minus 2 fifths. So in other words, A1 is equal to minus 2 fifths minus 9 twentieths A4. This next line here tells us A2 plus 0A3 minus 1 tenth A4 is equal to 1 fifth. That is, A2 is equal to 1 fifth plus 1 tenth A4. This last equation tells us this is A1 times 0, A2 times 0, A3 is equal to minus 3 fourths A4 is equal to 0. In other words, A3 is equal to 3 fourths A4. I have 1, 0, 0 that I want to write as a linear combination of 2, 3, 4, 9, 6, 8, 0, 1, 0, and 0, 0, 1. I said that A4 is equal to 1. That's this coefficient here. I said that A3 is equal to 3 fourths A4. That's this coefficient here. I said that A2 is 1 fifth plus 1 tenth A4. So that's going to be 1 fifth plus 1 tenth. So I get 3 tenths for A2. And over here, A1 is equal to minus 2 fifths minus 9 twentieths A4. So I get minus 17 twentieths. You can do the multiplication and add, and you can see that it will give you 1, 0, 0. So therefore, 1, 0, 0 is in the span of 2, 3, 4, 9, 6, 8, 0, 1, 0, 0, 0, 1. So now we can throw it out. And the new list we have to work with is 2, 3, 4, 9, 6, 8, 0, 1, 0, and 0, 0, 1. This is our new list. It's still too big. These are not linearly independent. We need to get down, because we're into F3, we need to get down to 3 vectors. So I'm going to repeat this process. I'm going to choose the vector, this next vector. I'm just going down the line trying to eliminate one more vector. So I'm going to try to express 0, 1, 0 as a linear combination of the other 3 vectors. So 0, 1, 0 equals A1, 2, 3, 4 plus A2, 9, 6, 8 plus A3, 0, 0, 1. I have my matrix, I row reduce using Wolfram alpha, and I get these equations for A1, A2, A3. I plug them in, so 0, 1, 0 is equal to 3/5, 2, 3, 4, minus 2/15, 9, 6, 8, minus 4/3, 0, 0, 1. You can verify this calculation is correct. So in other words, 0, 1, 0 is in the span of 2, 3, 4, 9, 6, 8, and 0, 1, 0. Which means I can throw it out, and now I have the vectors 2, 3, 4, 9, 6, 8, and 0, 1, 0. They still span F3, because the things I threw out, the 2 vectors I threw out, they were just linear combinations of my other 3 vectors. And these 3 vectors are linearly independent. You can verify, or you can trust me for now, and later we'll have a theorem, like, I don't know, a few chapters from now that will say that that's the case. And therefore, these 3 vectors is a basis for F3. Next, we have this theorem. Basis length does not depend on bases. So 2 bases for the same vector space will have the same number of vectors. We are not going to prove this theorem in this video, maybe in the next video, I don't remember. But we will go on to dimension. So the dimension of a vector space, notated with dim v, of a finite dimension vector space is the length of any bases of the vector space. In other words, the number of vectors in a vector space. And I'll give you one example as our closing example for this video. Here's our definition of dimension. That's the number of vectors in a vector space. So the dimension of Fn is equal to n, because the standard basis of Fn has length n. The dimension of the polynomials of degree m or less is m plus 1, because the bases, there is a standard basis for the polynomial space of degree m or less, and that standard basis is 1z, z squared up to zm, and it has length of m plus 1. And that's where we're going to stop. Dimension is where we're going to pick up in our next video. So to review what we talked about a basis of V is a list of vectors in V that is linearly independent and spans V. So the 2 criteria we had to show was linearly independent and that it spanned. We had several examples and worked them in detail. We also talked about, and like 2 videos ago when we talked about linearly independent and linearly dependent sets of vectors, we showed how to find whether or not a set was linearly dependent or independent. So in this video, we showed how to show a list of vectors spans a vector space. That is, we would take an arbitrary vector in the vector space and showed that it can be written as a linear combination of the vectors. And we did several examples. We had this theorem here, criteria for a basis. So a list of vectors in V, v1, v2 up to vn, is a basis for V if and only if every vector in V can be written uniquely as a linear combination of our list of vectors. We had the theorem for spanning list contains a basis. So every spanning list in a vector space can be reduced to a basis of a vector space. We had the theorem that a basis of a finite dimensional vector space, every finite dimensional vector space has a basis. And then we had the theorem of a linearly independent list extends to a basis. So every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis. We had this theorem that a basis length does not depend on the bases. So 2 bases for the same vector space will have the same number of vectors, which leads us to the definition of dimension. So the dimension, notated dim v, of a finite dimensional vector space is the length or the number of vectors in the basis of a vector space. So that's it for this video. Thank you for watching.